Hi everyone. In this lecture, I'll continue with the discussion of single stage amplifiers. So mainly in this lecture, we'll focus on common source or common emitter amplifiers. So in the previous lecture, we discussed a MOSFET as a current control device. So if you control the current between gate and source terminals, then if you apply a voltage between gate and source terminals, then you can generate a current between drain and source, which will vary in proportion to the gate source voltage. And again, we also discussed that an amplifier can be seen as a three-terminal device. Ideally, it's a four-terminal device, but if you can make one terminal as the common between both input and output, then it can be seen as a three-terminal device. Now, MOSFET, we have three terminals. So I can make two terminals as the input, and the third terminal will be the output terminal. And the order also matters. The order in which I choose the terminal also matters. So if I just blindly go by the number of possible combinations, it's going to be 3p2 combinations, which is 6. So if I choose uh, gate as the input, and there are two possibilities: gate source, gate drain, drain being common and source being common. If I choose source as the input, source gate and source drain, and drain source and drain gate. So these are the six possibilities. Now, if you understand a MOSFET device, it's a unidirectional device. If you apply a control voltage across gate and source, then a current is produced. So if I change the current, then we don't see a gate to source voltage changing. It doesn't operate in the reverse direction. Okay. So since it operates in the forward direction, so I'll eliminate all the possibilities that are related to drain terminal and even drain to source. So drain gate, drain source, and source drain. So we have to eliminate all the three possibilities. We are left with three combinations. So all these three lead to three different configurations. So for example, if a gate source, gate is the input, source is the common terminal. So that will be a common source configuration. The second term here will actually be gate is the input, drain is the common terminal. The way in which I've written is the first terminal is where you apply the input. The second terminal will be the common terminal between both the input and the output. So by that, the first gate source, when you apply input between gate and source, or yeah, at the gate terminal, then this is called the common source configuration. Okay, source becomes the common terminal. Okay, here we are going to take output at the drain. Okay, and similarly, gate drain. So you are applying input at the gate, and drain is common. So when I say common, that's where there is no AC signal variations on that node. You're going to fix the drain potential. Here, this is common drain configuration. And the third one, source gate. You apply input at the source, keep gate. I mean, you're not going to apply any AC variations on the gate terminal. In that case, we can call this as, that will be referred to as common gate configuration. So normally, how do you find which configuration it is? You just look at the amplifier structure. You see where the input is and you see where the output is. The third terminal will be the common terminal. So that's a standard way of seeing it. So now we will discuss about common source configuration. So your amplifier structure would be something like this. You're going to apply input between gate to source and the output will be between drain to source. Similarly, I'll draw the equivalent, its counterpart, the BJT counterpart. There it will be common emitter configuration. So this is Vi and V naught across the collective to emitter terminal. Okay. So again, when we defined an amplifier, we said there are three important parameters to look for. One is the intrinsic gain. So that is you don't load the amplifier with a load resistance and find that gain, intrinsic gain A naught. The input resistance R in and the output resistance R out. Okay. So these three determine the overall gain of an amplifier. So mainly we are going to use these MOSFETs as amplifiers. Okay. So these three parameters are very important. They determine the overall gain of the amplifier. So ideally, A naught is the intrinsic gain. If you don't load your amplifier, that is when you make source resistance as 0 and the load resistance as infinity, this is the gain that you're going to get. When you have a practical input with a finite source resistance and a finite load resistance, then you need to know the input and output resistance of the amplifier to compute the overall gain. Okay, at that time, you will have a loaded voltage gain. So again, I'll not focus much on the biasing of these architectures. I'll probably come back to that when we go to the design of an op-amp towards the end of this first part of the course. So right now we'll be only focused on the small signal analysis. So when I'm doing the small signal analysis, I'll just make this assumption. So I'll not actually be drawing the small signal models. So when you have a voltage Vi across the gate to source, we'll visualize a current flowing between drain and source. Of value, current would be Gm into Vi. Okay, Vi is the VGS, or rather, let me write VGS. So VGS will be the current flowing between drain to source. And we can also visualize R naught. Essentially, this is a small signal model. R naught is the resistance between drain and source. Similarly, if I apply a positive voltage at source and negative voltage at drain, so rather the polarity is reversed. I reverse the polarity of the input. Then what exactly happens in the circuit is there is already a DC current. I'll call it the drain quiescent current flowing in the circuit. But since we are applying a small input, which is wherein you are reducing the gate voltage slightly and increasing the drain voltage, that can be seen as a reduction in the drain current. So it will be the direction of the current will be minus Gm into Vi in this direction. Or for analysis purposes, we can just reverse the direction and say that the current is flowing from source to drain. If your source is at a higher potential compared to the gate, okay, then we'll analyze it as a circuit with current flowing from source to drain. Okay, these are very trivial points, but I'm just mentioning it for the sake of continuity when you analyze the circuits. So now we'll try to find the intrinsic gain of a common source configuration. So in a common source configuration, when we apply the input at the gate, source is grounded. So you'll have a current GMVI flowing from drain to source. Now the only path it has to flow through is the R naught. Okay, so I can assume that a current of value minus GMVI is flowing into R naught. Okay, if you have a GMVI flowing from drain to source, I can also apply KCL at this node and say that a current minus GMVI is flowing into R naught. So you'll have a gain of minus GM R naught into Vi. So this is your intrinsic gain. A naught is actually minus GM R naught. So you should notice that the sign is negative here. Okay, because drain and source will be in opposing phases. Sorry, gate and source will be in opposing phases. So which means there will be 180-degree phase shift between input and output. So if you apply a small sine wave, then you will expect a hugely amplified version of this signal, but there will be a 180 degrees phase inversion. Okay, and similarly, we'll find for a bipolar junction transistor. A bipolar junction transistor in a common emitter configuration, when I apply an input Vi, in a similar way, I'll assume the current GMVI flowing here, and the only path it has to flow through is its own R naught, so it will flow through that, and the voltage gain is going to be minus GM R naught, the intrinsic gain. Now we will compare MOS versus BJT. I've already very briefly mentioned about MOS versus BJT. For a given current, BJT always has a higher GM. We discussed that. But here we'll compare the intrinsic gains of MOS versus BJT. In a MOSFET, your GM R naught, your GM is actually given by the drain quiescent current upon V overdrive of the MOSFET, and R naught is given by 1 by lambda I drain quiescent current. So this you get the intrinsic gain as 1 by lambda into V overdrive. In a BJT, on the other hand, your GM is ICQ, the collector current upon VT. VT is the thermal voltage. Okay, it's 26 millivolts at 300 Kelvin into R naught, which is VA upon ICQ. So VA is the early voltage. So the intrinsic gain here is VA upon VT. If you look at this intrinsic gain, that's the maximum gain possible in a BJT. It is independent of the drain current or the collector current flowing in the circuit. Okay. So whatever be the collector current, you will get the same intrinsic gain for a bipolar junction transistor. Even if you vary the collector current, you won't see a gain change in the in the common in the common emitter configuration for a BJT. So this is the intrinsic gain. I mean, when you load it, of course, the gain will depend upon the current. But when you unload it, when you don't load it with uh, any load resistance, this is what you would get. Similarly, in the MOSFET, it's actually 2 by lambda VO drive. So here again, if you consider the drain current, your drain current is actually beta n into VO drive square. If you remember the lecture, I discussed about what is beta n and all that, the previous lectures. So your VO drive is actually 2 IDQ into beta n. Okay, so square root of this by beta n, sorry. Okay, so if you substitute it here in this expression, you will get the intrinsic gain to be, so what you can see is that the intrinsic gain, I'll just look at the proportionality, I mean, how is it dependent on width and the current. So if you fix your overdrive, let's say you change your current and WL ratios together, if you fix your overdrive, then your intrinsic gain will not change. Okay, your intrinsic gain will remain constant, and so this will be, so in fact, it is 2 by lambda into square root of, uh, in fact, that I can take the 2 inside, so you'll actually get 2 beta n upon IDQ. So your beta n is nothing but WL. There is a term, it's proposed W1 into mu n into Cox. And if you scale your current and width together, then you will actually not see any change in the intrinsic gain. So this is one. Okay. But you can see that if you keep your WL constant and if you increase the drain current, your gain will reduce. So this is again, let me remind you again, this is actually valid. I'm assuming that the MOSFET follows a square law device, square law characteristics. And this square law is actually valid only in strong inversion region. It will be not valid in weak inversion region. Okay. The other result that this shows here, the other the other interesting thing that this result shows here is that if you increase the width, the gain increases. For a given drain current, if you increase the width, the gain increases. What's happening is that for a given drain current, when you increase the width, your GM is also increasing, but your R naught is remaining the same. Okay, for a given drain current. In that case, again, you will see an increase in the gain. So all this is valid only in strong inversion region when the device follows a square law characteristics. Okay. Yeah. So these are the two important things, that the gain is proportional to root of W by L for a given drain current, or if you keep the W by L constant, then it's inversely proportional to the drain current, the quiescent drain current, the intrinsic gain. Okay. Yeah. So why do we care about intrinsic gain? Of course, when you're going to use this amplifier, especially in integrated circuits, we will normally have stages like this, wherein your load resistance will be a PMOS. A PMOS in case of it might be biased with some bias voltage here. I'll just draw the AC model. So drain gate will be at AC and source will also be at AC. PMOS device. And similarly for a BJT, bipolar junction transistor, you can actually have a PMOS load, a PNP transistor load. So again, this is AC ground, emitter and base are at AC ground. In that case, we'll see what happens. Why are we interested in finding the intrinsic gain? This is something you will encounter, especially when you have a multi-stage amplifier. The intermediate stages might contain stages like this. Now, the gain of this guy is actually given by, so you again, they looking in impedance here, it's going to be R naught, R naught PMOS, and R naught NMOS. They both will come in parallel. So the gain is in that case is going to be simply GM of this guy, because input is only applied to this. There is no input applied to the source, to the PMOS device, which is in the load. It's going to be GM into RON parallel ROP with a minus sign. Okay, because you will see both that this is also towards the ground and this is the common terminal. So RON will appear in parallel with ROP. So you're going to get this, and then you will have GM into pi IDQ into 1 by lambda NMOS and 1 by lambda PMOS. Okay, so this result GM over IDQ will be, so we know your GM is 2 IDQ upon VO drive. So GM upon IDQ will be 2 upon VO drive. So this result here will reduce to 1 by lambda n. You'll actually have a harmonic mean. So 1 by lambda n plus 1 by lambda p. This is the expression for gain when you are loaded by a PMOS load. Okay. So in a similar manner, you can also find the gain for a common emitter configuration. You can very easily show that when you have two amplifiers, when you have a PNP transistor loading this, you're going to get a GM of ICQ upon BT into R naught ROP parallel RON. Okay, it's going to be ROP parallel RON. So I can write it as 1 by ROP plus 1 by RON. So this is PNP and NPN transistor resistance with a inverted again. So you'll get a very similar result. You'll be left with there will be ICP will be cancelled out. ICP will be cancelled out, and you will be left with 1 by VT into VA VAN. I'll write it as VAN and VAP by VAN plus VAP. So this is the voltage would be. This is the expression for gain that you will be getting here. Again, if you see this expression for gain, intrinsic gain of a PNP transistor, it is independent of the uh, bias current, the quiescent collector current or the bias current with which both the devices are biased. Okay. Whereas again, the same relationship holds here. For a common source configuration, the gain does depend upon the bias currents and the W-L ratios. Okay, because it depends on VO drive, which in turn depends upon the bias current and the W-L ratios. Okay, so that's it about the intrinsic gain of common source configuration. Now I'll just briefly discuss about. I think yeah, just one point which I missed is how do you measure the input and output resistances? So when you have an amplifier is a four-terminal device, to measure the input and output impedances, if you are measuring the input impedance, you should ensure all the independent sources in the circuit should be made to zero, and then apply a small AC signal, okay, at the terminals where you are trying to measure the impedance and measure the current through it. Then the ratio of VI by II will give the impedance in between these two terminals. Now, why do we turn off all the voltage, I mean, all the independent sources everywhere else? It's that because we don't want to see the influence of any other energy providing element in the circuit. Okay. We only want to study the impedance between these 2 points when you're loading, when you're powering this input terminal by a voltage source. Okay. So that's why we turn off all the other sources. And similarly, output impedance can be measured by shorting the input. Input should be made to zero. Input AC source should be made to zero, and your R out, you should apply a test voltage, say Vx here, and measure the current that is flowing out here. So I can say Vx by Ix, provided you are making the input equal to zero. Input is now an independent source. You should ensure that that's not driving, because if your input is driving, then the current that you will be measuring will also be due to the input. You don't want all that. If you're measuring the output impedance, it is the response of this circuit to variations at the output terminal. So only that should be seen. So every other source you will try to make it to zero. Okay. So that's how you measure input and output resistances. And I haven't done it for these two circuits. For a common emitter configuration, for essentially you're looking into the gate of a MOSFET, the input impedance is obviously infinity. Okay. And for a BJT, you're looking into base and emitter terminal, and you're looking into the base terminal, and the voltage is applied across base emitter. So it will be simply R pi for a BJT. And the output resistance for both the devices, you're going to short the gate and you're going to short the base for a for a BJT, and you're going to look at the drain and collector. So that will be simply R0 for both the devices. Okay. So on R0, if you increase the drain current, R0 is going to reduce. In a MOSFET, R0 also has a dependence on the channel length. So increase the channel length and you will see an improvement in the output resistance R0. Okay. So this is it about common source configuration. That is to know. That's again, these are all, most of you, if you have taken a circuits course, you by now know all these things. Okay. The one thing that I wanted to stress in this class is how do we measure intrinsic gain of a common source amplifier? So we said we talked about intrinsic gain. So we'll have a setup to measure the intrinsic gain of a common source amplifier. So here I've also shown capacitors. This test bench was drawn the schematic to measure the frequency response. So we don't really care about the capacitors here. Okay. We'll only, what we do is you need to connect. First, you have to configure the device in common source configuration. And in this setup, I'm doing a current source biasing. Okay, I need to fix the current and study the amplifier. Okay, so first the only difference is you need to connect a set resistance between drain and gate terminals. So for example, let's say if I were to study the intrinsic gain, I can do something like this. I can force a constant current I into this device and maybe apply a DC voltage plus, and then I can apply a small AC signal here and try to measure the voltage at this point. Okay, but I can't do a biasing. This is some VDC. So it will be equal to the quiescent VGS necessary. to maintain that current. The problem with this setup is that when the MOSFET operates in saturation region, it's supposed to behave like a current source. So therefore, I have a current source I here, and then a MOSFET also acts like a current source. So the problem is I can't connect two current sources in series. So that's why this biasing will not work. And when I say I've biased MOSFET, all the three terminal voltages should be defined, clearly defined. So your gate here, the voltage is defined with respect to ground. Source is anyways grounded, so gate and source are defined. The drain voltage in this circuit, for an ideal MOSFET, if you use the square law characteristics without a dependence on drain voltage, then yes, it's not defined. Okay. So, which is why, especially, it might work in a simulator, of course. It might work in a simulator, but when you make even some small changes in the width, you will see suddenly a big changes in the, the operating point of the circuit. So, which is why this is not a very good way of biasing your circuit. So then, how do we bias it? I want to do a current source biasing. Okay, in a simple way. Of course, you can use also some feedback mechanisms to do that, to do the biasing. But let's say in a very simple way, we want to do the biasing. We don't care about the noise and other things. The simplistic way to bias is just add a resistor between gate and drain terminals. Now we know no current can flow through the gate terminal. So the voltage drop, the voltage potential. So in this circuit, your VDS and VGS, the quiescent operating points will be same. Okay, since no current flows through the resistance, this terminal and this terminal will be at same potential. Then you can AC couple your input through a capacitor. Now, why do we need RB? I mean, I might as well have shorted the two. The reason why is that if I short the two, then these two terminals are electrically shorted. Okay. RB, in a way, isolates the two terminals at AC. At AC, it provides you a good isolation. Okay. So if you see the circuit here, if I'll just do a quick analysis of this circuit. If you see the circuit, it actually has two paths to the output. So when I apply, so this is RB, and I'll assume that there is an R0 of the device. I'm again trying to find intrinsic gain, so there is no real load resistance. So when I apply input here, an input can direct, because it's a resistor, you will have a direct path from here to the output. See, the current that flows into R0 will determine our gain. Okay, and there is also a current coming from the device itself. So there is also a current coming from the device, which is GMVI. So there are two paths for the current. If your RB is sufficiently large, if I make ideally say RB as very large, so when I say RB large, the resistance value RB should be much greater than R0. So you can estimate R0 from simulations. If it's few kilo ohms, then you can choose RB as few mega ohms. Okay. Then I can ignore this path, the path through RB. Okay. Then the gain will simply be, and also you should look at it this way. The gain will simply be, let me just derive the gain for that, then you will understand what I'm saying. So you have a current GMVI flowing here, and you have R0 here, and there is RB here. So to analyze the circuit, I'll apply superposition. I'll assume that, of course, the input is same to both the points, but I'll assume that I'm applying two identical inputs at two different points in the circuit. You can treat it like that, okay? And to find the gain, I'll first short this, okay, and apply superposition to find the gain for the circuit. If I short this, then when you apply VI, the gain at this point due to this input, it's going to be minus of GM into RB parallel R0. That's the gain because of this VI. Now, I'll ignore the path to the MOSFET. I'll ground this and apply input here. Then this is going to be plus R0 by R0 plus RB. Okay, so these are the two paths that you will actually get for the gain in the circuit. Okay, now, yeah, so now in this expression, if we can quickly rearrange the terms, you will actually get 1 minus GM RB into R0 by R0 plus RB. Okay, or you can look at directly from this expression. If I choose RB much greater than R0, so this term will just become minus GM R0, and the second term will just vanish to 0 if RB is much greater. Okay, the second term will simply vanish to 0. So that's how you derive the gain for the circuit. You will get a gain like this. since GMRB is much greater than 1, so you will actually have this gain to be negative. I mean, you might wonder common source gain has to be negative. So why is this? This is 1 minus something. So GMRB is much greater than 1, so this should be negative. Okay, this term will be less than 0. There is other way of deriving this as well. So what I normally do is that you can treat R naught as an output impedance as a separate resistor and quickly try to find the Thevenin equivalent of this circuit. So if I apply Vi here, I'm just interested in finding the Thevenin equivalent and represent it by its Thevenin equivalent. Okay. So when you represent it by its Thevenin equivalent, I'm just looking at this point. So you have a current GMVI coming here. Now GMVI doesn't have, if when I find Thevenin equivalent, I'll ignore R naught. Okay, I'm trying to see what is the equivalent of the circuit as seen by R naught itself. Then this GMVI has to flow through this. So it will develop a drop of GMRBVI. Okay, it will develop a drop of GM into RB into VI across this. And this node voltage is Vi. So the voltage V0, if you apply KVL in this loop, there is a loop here, VDS, VGD, and VGS. Okay, then your V0 is simply going to be minus GM RB into Vi plus Vi. So you will get 1 minus GM RB into Vi. So this will be your output voltage. And to find the Thevenin resistance, how do we do it? Is we just short the input and find the resistance seen at this point. Now I've removed R0 from the device. Okay. So if I short the input, you'll simply get the Thevenin resistance to be RB. Because the R0 is not included in the device. GMVI is 0 because input is 0. There is no current flowing between drain to source of this MOSFET. So if I apply any voltage, test voltage here, the only equivalent resistance seen will be because of RB. So the Thevenin model for this circuit is going to be 1 minus GM RB into Vi and a resistance of value RB. So this is the equivalent circuit that will be seen by R0. So from this, the gain of this circuit is going to be 1 minus GM RB into R0 by R0 plus RB. So this will be your intrinsic gain for this circuit. If you choose RB much greater than R0, okay, RB much greater than R0, then you will get this result to be approximately equal to minus GM R0. Okay, so this result will simply reduce to RB is much greater. So this term will be minus GM RB. Okay, and this term will simply reduce to R0 by RB. Because RB is much greater, I'll ignore R0 here. So you'll get, and this will turn out to be equal to minus GM R0. Okay, so that's how you get it. So using this setup, you can actually measure the intrinsic gain of an amplifier. So I'll just quickly show the setup here. So using this, you can apply your input, AC input at this point. Okay, so you don't have to worry about the DC, what is the DC you have to apply for the input. You can apply 0 DC input because I've capacitively coupled it at this point. So you can apply the input here and take the output at this node. Okay, then you will get the intrinsic gain. So RB is there mainly to provide isolation between input and output. Okay, if RB was very small, you should carefully choose RB. Then if RB is sufficiently large, much greater than R0, then you can directly measure the intrinsic gain. So this setup allows me to increase the bias current and the dimensions, study this intrinsic gains variation, especially in devices always in saturation region, because your gate and drain potentials are at the same voltage. Okay, gate and drain are at the same potential. Now you might also want to have gate and drain to be at different potentials. That can be very trivially done. So once you have the circuit, so all you need to do is just add a DC voltage. This is only for simulation. A DC voltage, let's call it Vx here. So this is RB. Again, no current flows through this. There is no gate current in the MOSFET. So here VDS, previously VDS quiescent point was equal to the quiescent VDS voltage was equal to the gate to source quiescent voltage. Okay, but now you'll also have to add Vx to this. You can just apply KCL in this loop. So this is VGS quiescent, and the drop across the RB is 0. DC voltage is 0. Okay, so you get this. So this way, I can Vx is a DC voltage source. I can vary the voltage of DC Vx and ensure that VGS and VDS are at different voltages. So then you can measure gains at different bias points for VDS and VGS. Okay, so this is another setup, to, a very simple setup to measure the intrinsic gain of an amplifier, common source amplifier. Okay, so now that we are done with the discussion about intrinsic gain, so what happens when you load it? When you load a common source amplifier, what happens to the intrinsic gain of a common source amplifier, or the overall gain of a common source amplifier? So we can see if your input is applied, so we'll also have to apply a source resistance, RS, and so I'll call it VS here. And this is the overall amplifier. So now the input resistance is infinity. So the input appearing here is also Vs. And we have a current GMVI flowing here. And R naught will appear in parallel with RL. So you can say the gain is going to be minus of GM. Again, you can assume this as a current minus GMVI flowing into the load resistance. So minus of GM into R naught parallel RL. Okay. So this can be rewritten as minus GM R naught into RL by RL plus R naught. So this is the loading factor, if you remember from the previous lectures, and this is your intrinsic gain. Since your Rin is infinity, the factor before that RS has no effect here. The overall DC gain of the circuit, RS has no role here, the low frequency of the DC gain. The bipolar junction transistor, the only difference is you have an input resistance of R pi. So when you apply Vs, the voltage at this point is going to be R pi upon R pi plus Rs. Okay, that what gets multiplied by minus GM R naught into RL by RL plus R naught. So this will be the expression for the common source gain when you load for a common emitter configuration, when you load it with a finite load resistance, and you also drive it with a source with a finite source resistance. Okay, so here you can see both the input and the output ports, because they have finite load resistance, finite R naught and R pi. Okay, input and output resistances. You'll see a reduction in the overall gain from its value of from the value of its intrinsic gain. Okay, so this is all about common source configuration. So as I said, this is more of an introductory videos on common source. So as we proceed, if it's too trivial for some of you, you can skip these videos, and I'll quickly go to the frequency response. Okay, but the intrinsic gain test setup is pretty useful, especially before you start amplifier design. I normally do that, so that gives me an idea as to what is the fundamental gains for different device lengths and bias currents and WL ratios. What is the gain that I can expect from this technology for any given technology? Okay, yeah, I'm not sure again if I can present cadence results again. I don't want to. I'm not sure if which is legally permitted for me to present on an online platform like this. So I'm not showing any cadence simulations, but you can just very easily simulate it in any technology file that you have access to. This is the setup that you can use for measuring the intrinsic gain here shown. Okay. So fine, in the next lecture, I'll start with the discussion of common gate amplifiers, and probably we'll actually solve some problems on common source in a late once I finish all the discussion on basic discussions on single stage amplifiers.